Hey everyone, and welcome to this explainer. If you're on a procurement team, maybe you're an electrical engineer or a facility manager dealing with some truly high-stakes infrastructure, you are absolutely in the right place. Today we're taking a microscopic look at the actual physical and chemical forces acting on your cable tray installations, and more importantly, how you can defend against them. You know, we so often think of metal infrastructure as just static, immovable, permanent, but let's be real, the reality is way more dynamic than that. Let me just kick things off with a question that really challenges a super common assumption in our industry. Is simply locking your cable tray enough? You bolt it down as tight as you can to the support bracket, you make absolutely sure there's zero wiggle room, and you walk away assuming the whole system is perfectly secure. I mean, it kind of feels like the safest approach, right? Well, I've got to issue a bit of a warning right up front. Believing that just locking a tray down guarantees its safety is a massive misconception, and honestly, it's one that can cost a facility dearly. Because think about it, if you lock a system down completely, you're totally ignoring the real hidden villain of structural destruction, which is thermodynamics. And when you ignore those forces, the consequences get violent. Just imagine thick metal trays physically warping out of shape, structural supports violently twisting under immense pressure, and heavy-duty splice plates literally snapping right in half. It's just the raw physics of it all. Expanding steel can exert thousands of pounds of pressure per square inch. This isn't just some theoretical classroom stuff. This is exactly what happens when immense physical energy has literally nowhere else to go. Okay, let's dive into this. We've got a structured roadmap today to help you defeat these threats and guarantee long-term safety. First up, the hidden installation threat. Second, hold-down versus guide clamps. Third, mastering thermal expansion. Fourth, preventing galvanic corrosion. And finally, meeting global safety standards.
Section 1. The hidden installation threat, and exactly why simply locking things down is going to fail.
The truth is, there are invisible forces actively working against your infrastructure 24/7. In fact, our source material drops this absolute core truth right out of the gate. Simply locking the tray to the support bracket isn't enough. You really just have to let that sink in for a second. A single oversight in how you install and secure your system, something as innocent-looking as just over-tightening a single bolt in the wrong spot, can trigger catastrophic system failure down the line. No way around it.
So what exactly are these invisible forces? Well, we're talking about thermal expansion, thermal contraction, and the structural stress accumulation that comes with them. Metals naturally expand when they get hot and they contract when they get cold. If your entire system is rigidly locked into place, that metal still absolutely needs to move. But because it can't, it basically turns its own kinetic energy against itself. It just accumulates and accumulates structural stress until the absolute weakest link, which is usually those splice plates, just tears apart. You've essentially taken a rigid system and turned it into a self-destructing one.
Moving on to Section 2. Hold down versus guide clamps, and how to choose the right defense.
And this brilliantly illustrates the difference in how we actually fight back. These two clamps are the unsung heroes of our whole story. On one side, you have hold-down clamps. These are specifically designed for rigid support, locking the tray firmly and permanently in place. But then on the other side, you've got expansion guide clamps. These are engineered specifically to allow for sliding movement. So, they hold the tray completely secure laterally, but they let it glide smoothly longitudinally as that metal expands and contracts. For all the electrical engineers and procurement folks watching right now, knowing the difference between these two clamps is absolutely your ultimate defense. A simple oversight in clamp selection directly leads to failure. If you go ahead and specify a rigid hold-down clamp in a spot where an expansion guide clamp should obviously be, you are essentially building a ticking time bomb of structural stress. Knowing the difference and knowing exactly where to deploy each one is completely non-negotiable.
Section 3. Mastering thermal expansion. Basically, engineering our systems to actually breathe.
So this is where we take those clamps we just talked about and apply a real tactical strategy. We have to shift our mindset from, let's just lock everything down, to actually engineering the system to breathe. And there's a crucial step-by-step chronological logic to how you do this. Step 1. You must position your anchor point securely. You use your rigid hold-down clamps right here to establish a solid zero-movement baseline. Then, Step 2. You set your sliding points using the expansion guide clamps. By strategically placing these sliding points all along the tray's run, you actually give that thermal expansion a safe place to go. You're relieving all that structural stress by letting the metal naturally expand and contract without snapping the joints.
Now, you might be wondering, what's the big takeaway here? Why does this matter so much? Well, the benefits are absolutely monumental. Executing this exact procedure prevents structural stress, and it ensures the long-term safety of the entire system. And, incredibly, it also mitigates high vibration and seismic risks. Think about it. When the Earth literally shakes, or when heavy industrial machinery is vibrating nearby, a system engineered to breathe can absorb and naturally dissipate all that kinetic energy. A rigidly locked system, on the other hand, is just going to crack.
All right, Section 4, Preventing Galvanic Corrosion. Now we're dealing with a chemistry problem.
Now, what's really interesting here is the hidden chemistry. We've talked about physics, but now we're pivoting to a silent, completely invisible chemical threat, galvanic corrosion. This happens when two totally incompatible metals touch each other in the presence of an electrolyte, which could just be normal ambient moisture in the air. They essentially create a battery, which, is great if you're trying to power a flashlight, but it is terrible if you're relying on those metals to keep a massive ceiling tray from collapsing. One metal rapidly degrades the other, and those perfectly placed clamps you just installed, they will just silently rust away, totally compromising your structural stability.
So for our procurement teams, this right here is basically a quick reference guide that can literally save you millions in replacement costs. You absolutely must specify the exact right material for your clamps. If your facility uses hot-dip galvanized or HDG trays, you need chemically compatible clamps, period. If you're operating in a highly corrosive environment and you're using 304 or 316 stainless steel trays, your clamps absolutely must match that exact metallurgical profile. Mixing the wrong metals is just an open invitation to galvanic corrosion.
Finally, Section 5, Meeting Global Safety Standards. This is where we look at SINMA's holistic approach.
Let's bring all this theory back down to earth for a minute. When we talk about high-stakes environments, we're talking about facilities where failure simply is not an option. Shanghai Sinma Busway and Cable Tray Company, or just Sinma, builds intelligent cable management systems designed specifically for the most demanding sectors on Earth. We're talking massive data centers handling critical information, complex rail transit systems moving thousands of people every day, heavy industrial plants, and massive commercial buildings.
And they don't just, rely on some good engineering theory and call it a day. They actually prove it through incredibly rigorous global certifications. Their products comply with standards like IEC 61537, NEMA VE1, BSEN 50085, and GB 311251. By strictly adhering to these international benchmarks, it essentially guarantees that these solutions are fully tested for the absolute ultimate in seismic, structural, and environmental stability. Because at the end of the day, true safety isn't just about finding one good clamp. It's about a comprehensive solution. And that's exactly what Shinma provides: cable tray systems, busways, seismic bracing, and intelligent cable management. Every single component, from those rigid hold-down clamps we discussed, all the way to the stainless steel sliding guides, is brilliantly engineered as a holistic ecosystem, designed to work together flawlessly. So, as we wrap up this explainer today, I want to leave you with one final, truly provocative question. Something you should absolutely ask yourselves and your engineering teams tomorrow morning. Next time you look up at the infrastructure powering your facilities, ask yourself, are your cable systems engineered to breathe, or are they destined to snap? Thanks so much for hanging out with me on this one, and as always, stay curious.